Here we'd like to examine the polarity of individual bonds within a molecule, and then we also want to make a decision about the overall polarity of the molecule. We have these three rules of thumb, and the rules deal with electronegativity differences between two atoms. There's a table for this right here, which shows the electronegativities of various elements. Whenever we have a bond between two elements, we want to see what the difference in electronegativity between them is. And that can tell us about the type of bond that they'll form. So for example, in this first one, where beryllium is bonded to two hydrogens, we could look at the electronegativity difference between beryllium and hydrogen, and that could tell us whether the bond between them would be expected to be polar or nonpolar. So let's see, beryllium has a electronegativity of 1.5. Hydrogen has an electronegativity of 2.1. So I could write those next to the atoms if I'd like. Now we can subtract two of these to see what the difference is. So 2.1 minus 1.5 gives us 0.6. And it's going to be the same over here. So we want to go to the rules of thumb now and see what that tells us about the bonds. A general rule is if the electronegativity difference turns out to be 0.4 or less, then what we have is considered a nonpolar covalent bond, meaning the electron is largely shared equally between the atoms. If we find, as we did in our case, that the electronegativity is between 0.4 and 1.5, then what we have is called a polar covalent bond. That's what exists between hydrogen and beryllium. If we get an electronegativity difference greater than 1.5, then it's called an ionic bond, and the electron is largely donated to the other element, not shared so much. So these are both going to be polar covalent bonds. Now that we know they're both polar covalent bonds, we can signify this not by writing it, but by using a symbol, which is a Greek letter delta. And we want to put either a minus or a plus, depending on which atom turns out to be slightly more positive than the other. So the atom which has the higher electronegativity attracts electrons more strongly than the one with the lower electronegativity. So what this means is that hydrogen is going to be the element that the electron tends to hang out near more. So with that in mind, what we'll do is we'll put a delta negative on hydrogen. And we want to put a delta positive on beryllium. The electron is more attracted to hydrogen than it is to beryllium, so that leaves hydrogen with a slightly negative charge when that electron is hanging out near him more than beryllium. Same thing would happen with this hydrogen. We would have a delta negative there because in that bond the electron's going to hang out more near the hydrogen than the beryllium. Now, after doing that, we have to decide what is the overall polarity of this molecule. And we want to take into account the geometry that we had looked at recently in our past analysis. So in the past analysis, I said that this molecule would be considered linear. And it comes from the idea of these electron groups wanting to be as far away from each other as possible. that we would get a 180-degree angle between them. Now, the polarity of the bonds there is not going to change the overall shape of this molecule. And so this molecule is going to be linear, with a negative side to it on this hydrogen and another negative side of it on the other hydrogen. And so if you do have an object, which is basically like a stick, with a negative here and a negative there and a positive in the middle, we want to see, is there any asymmetry in this situation? Well, you could think about yourself standing near the molecule. And you want to think about, like, is it different for me if I stand on this side of the molecule versus the other side? If it is very different on one side versus the other, then you'd have what's called a polar molecule. But here we see that this person is standing near a negative, and this person is also standing near a negative. So there's actually symmetry to that. And it's not going to be any different if you're standing on one side versus the other. For this reason, we're going to say that the overall molecule is nonpolar. All right, so that answers that one. Let's take a look at CO2. We better go to the electronegativity table and see the difference between them. All right, carbon has electronegativity of 2.5, oxygen has 3.5. That's going to be a difference of 1.0. According to these general rules of thumb, we would be between 0.4 and 1.5. So again, we have a polar covalent bond. So I'm just going to do the same thing that I did above. We have a negative side there of the bond, and we have a positive side here, and we can do this for the other bond. First you analyze the individual bonds, then you analyze the overall molecule. So when it comes to this molecule, for the same reason as above, it is going to be nonpolar. But now let's check out when hydrogen is bonded to a carbon and a nitrogen. We know from our previous investigation that this is a linear molecule with 180 degrees between the electron groups. Let's check out the electronegativity of nitrogen. Nitrogen has an electronegativity of 3, carbon was 2.5, and hydrogen was 2.1. Alright, so it looks like the bond between carbon and hydrogen would have a difference in electronegativity of only 0.4. And according to the general rule of thumb, if we do have a difference that's 0.4 or less, we will not consider that polar. It's going to be called nonpolar. This molecule will have a polar bond, though, between the carbon and the nitrogen, because that difference was 0.5, which is a little bit larger. So that makes this a polar bond. Now the nitrogen is going to have the higher electronegativity, so it would be expected to have the negative side of the bond on itself, and the positive side of that bond would be on the carbon. Now, is this molecule considered polar or nonpolar? It is polar. This is a polar molecule. Why would I say that? Because it is different if you're standing on one side of the molecule versus the other. If you're over here, you're near a negative side of a bond. You're at an element that has an electronegativity of 3. But if you're over here, you're attached to something which has an electronegativity of 2.1. Big difference there. And even though this bond may be considered not a huge electronegativity difference, it is still on the positive side of this bond. So overall, this could be considered the positive side of the molecule, and this could be the negative side. So I would say it's a polar molecule. Okay, when it comes to the BCl3 molecule here, we want to, first of all, take a look at the geometry of it. It's trigonal planar, meaning that all the atoms reside in one plane with a 120-degree angle between the bonds. So there's a radial symmetry to that. So if you're standing on this side of the molecule, you'll be near a chlorine, for example. But if you stand near this side of the molecule, you're also by a chlorine, even if you're down here. The molecule appears the same to all these three people. And so, because of this symmetry, no matter what, even if the bonds are very polar, in this case, this is going to be a nonpolar molecule because the bond polarities would cancel out. Let's see what the electronegativity difference is between boron and chlorine. All right, boron's got 2.0 for its electronegativity. Chlorine has 3.0. That's a difference of 1. So these actually are polar bonds. And we can just signify that with our delta here. Chlorine is going to be the more negative of the two. And we can just put, a single delta positive here by boron. But yeah, like I was saying, you're going to have a negative side of the bond on all three of these terminals, so this is going to be nonpolar. Yeah, so just to make sure that that's clear, we're talking about the molecule itself here, not the individual bonds. The individual bonds are polar. All right, sulfur dioxide. Sulfur's electronegativity is 2.5, oxygen is 3.5, so that's a difference of 1, which means that these bonds are polar. In this case, oxygen has the higher electronegativity. So let's put a delta negative on the oxygens, and we'll put delta positive on the sulfur. And so this is a different kind of situation. This is a bent molecule rather than a linear one like we had above. So in the linear case, I said if you were on one end of the molecule versus the other, the molecule would appear the same to you. But would that really be the case for sulfur dioxide? Well, if you're standing here, then things would look a little different from a person who's standing over here. See, the person who's standing on this side is really nearest to two negative terminals. But the person that's by the sulfur atom is near the positive side of the molecule. And that's the idea, is that there is a positive side and a negative side to this situation. For that reason, we're going to say that this molecule is actually polar. It has polar bonds, And because of the geometry being bent like that, it does allow one side of the molecule to be positive and the other end of it negative. So this is a polar molecule. Let's take a look at one of these tetrahedral molecules. This one is 1 carbon and 4 hydrogens. Now, carbon had an electronegativity of 2.5, hydrogen 2.1. That's a difference of 0.4. Now, some texts would say that that is just very slightly polar. Some would say it's considered nonpolar. So I'm going to say these are largely nonpolar bonds. If these are considered nonpolar bonds, then generally, in most all cases, nonpolar bonds result in a nonpolar molecule. Even if they were polar bonds, though, it would still be considered a nonpolar molecule because it would be the same if you're standing here versus standing over here. Either way, you'd be near a hydrogen, and even if you were up top, you would still be near a hydrogen. Because of the symmetry of the molecule, any polarity in the bonds would cancel out and make the overall molecule nonpolar. Let's take a look at NH3. Nitrogen has an electronegativity of 3, and hydrogen has an electronegativity of 2.1. That is a significant difference there. It's 0.9 of a difference. So that's going to definitely be a polar bond between nitrogen and hydrogen. Nitrogen will represent the negative side of those bonds, and each of these hydrogens can be a delta plus. But now we have to examine the molecule overall. If you're standing on this side of the molecule, you're near some positive ends of bonds. But if you are standing over here, you are now near the nitrogen, which is the negative side of those bonds. That's a difference. And so we're going to say that there is a dipole moment to this molecule, meaning it has a negative and a positive side to it. So we'll call this a polar molecule. All right, here we have oxygen bonded to fluorine. The difference between them is 0.5, so that's just slightly polar. And for the same reason as the above, we would say that this is also a polar molecule. Now, fluorine has the higher electronegativity, though. So that's going to make this the negative side of the bonds, and oxygen will be the positive side. With water, we find that the electronegativity difference is significant. The difference between hydrogen and oxygen is 1.4. That's a lot. So strongly polar. We're going to have the negative side is the oxygen. Hydrogen is going to be the positive side. And yeah, this leads to certain types of phenomena we see, such as hydrogen bonding. That's where one molecule of water can be attracted to another molecule because of the polarity of the molecules. And so what ends up happening with hydrogen bonding is we see that one of the oxygens of one molecule will be attracted to one of the hydrogens in the other molecule. And we show that with a dash. Because it's not a real chemical bond, it's just an electrostatic attraction between the two.